everyone, it's George here, and I'm happy to be teaching about quantum mechanics to you today. Click on the link in the description if you want to see the video about waves and particles. Anyways, let's get started. Our first topic of the day is the Max Planck and the Blackbody radiation problem. A little insight on our friend Max, if you forgot who he was. Max Planck was a famous German physicist who was best known for his constant H. So what is a blackbody? A blackbody is a physical body that absorbs all incident electromagnetic radiation that comes near it. An example of a blackbody can be a furnace. If there is a small hole somewhere, that means heat energy can enter from the outside. Physicists were studying a blackbody and they soon realized the problem. They first theorized that the blackbody follows the classical physics laws, which is that a blackbody at thermal equilibrium will emit an unbound quantity of energy as wavelength decreases, which corresponds to the ultraviolet light. When this didn't happen, physicists were left dumbfounded by the abnormality. And take a look at the graph on the right, in which the blackbody intensity dropped to zero at both sides of the wavelength. Fortunately, our friend Max Planck comes to the rescue and solves the problem in 1901. He first proposes that energy in a blackbody comes in quanta, which means stored in small packets of energy. Planck also stated that each energy in quanta depends on frequency, which is denoted by F, and H, which is the universal constant. This was also known as Planck's blackbody radiation theory, and it worked. Max Planck also won a Nobel Prize in 1918 for his energy quanta discovery. Props to him. And let's move on to the second topic. Now I'm going to be talking about the significance of E equals HF. And the person of significance in this topic is none other Albert Einstein. And you probably already know him, so I'm not going to introduce him. And the formula E equals HF is also known as the Planck-Einstein relation. H stands for Planck's constant, which is also equal to the value of 6.63 times 10 to the power of negative 34. And F is the frequency. Einstein first proposed the idea of photons, which have unique properties that differ from classical particles. Each photon also contains a parcel of energy. The formula of E equals HF is significant because it solves the problems that were associated with the photoelectric effect. It shows that the energy of a photon depends on the light frequency and not the intensity. If the energy of a photon is less than a work function, even a high intensity light won't even be able to eject electrons. Einstein also theorized that when a photon falls on a piece of metal, all of the energy of the photon is transferred to the electron. Some of the energy is then used to remove the electron from the metal, and the rest of the energy is given to the ejected electron as kinetic energy. But don't worry, there's a dedicated topic about the photoelectric effect coming up. Don't miss it. Now let's move on to the third topic of the day, wave-particle duality and the double-slit experiment. The key person for this topic is Thomas Young, who was a British polymath, and he was the first one to conduct a double-slit experiment when he was a young lad. Well, what is wave-particle duality? It is a key concept in quantum mechanics that every quantum or particle entity can be described as a particle or a wave. It expresses the inability of the classical concepts of particle or wave to fully describe the behavior of quantum scale objects. The double-slit experiment was first conducted in 1801, and how did the experiment work? In the double-slit experiment, the two slits are illuminated by a single laser beam. If the width of the slits is small enough, like less than the wavelength of the laser beam, the slits diffract the light into circular waves. As a result, the experiment proved that both light and matter can display both particles and classically defined waves. characteristics, which at first it was originally that it could only display one characteristic. And you could take a look at the picture on the right for a visualization of the experiment. The fourth topic of the day is going to be the photoelectric effect and Einstein's explanation. The key person for this topic is Heinrich Heinz, and he was the first person to understand the photoelectric effect. However, Albert Einstein was the first person to fully understand it. Well, the photoelectric effect is the emission of electrons when electromagnetic radiation, such as light, hits a material. The electrons that were emitted are called photoelectrons. It was discovered that if the light's frequency is below the threshold frequency, no electrons will be discharged. But if the frequency is above the threshold, the kinetic energy of the ejected electrons varies in a straight line. This result left physicists confused even when they refer to classical physics laws. And there are two problems. Number one, electrons should be able to discharge when the light intensity is sufficiently increased, but it did not work out. The second problem is that the kinetic energy of the electrons should increase if the light intensity were to also increase. This did not prove to be true as well. All hope seemed to be lost until Einstein came up with the formula E equals hf and with Planck, and this was explained before, and some of these points on this slide will not be brought up. They're brought up previously, and yeah. But Einstein made a few key points such as if the energy of a photon is smaller than the work function, no electron will be emitted no matter how high the light intensity is, and it instead depends on the frequency. Einstein's photon theory also proves that the kinetic energy of a photon is equal to the energy passed. Some facts about the photoelectric effect were also explained previously. For Einstein's work on the photoelectric effect, he was awarded the 1921 Nobel Prize for Physics. And as a bonus, I'm going to be solving an example photoelectric problem. So the question is, copper is used in a photoelectric experiment. The work function of copper is 8.17 times 10 to the power of negative 19. Calculate the minimum photon energy and frequency needed to emit electrons. So we know the work function from the graph, which is for copper, which is 8.17 times 10 to the power of negative 19. And we know the value of Planck's constant, which is 6.63 times 10 to the power of negative 34 joules per second. And we need to find the lowest energy, denoted by E photon, that photons must have to cause the emission of electrons of frequency F. And the lowest photon energy must satisfy the equation E photon equals W. And this function corresponds to frequency in the equation E photon equals W. And we solve from there. So we know the work function of copper is 8.17 times 10 to the power of negative 19. And now we solve for frequency, which is E photon over H, or Planck's constant. And we plug in the numbers for that. So the value of E energy of the photon is 8.17 times 10 to the power of negative 19. And divide that by Planck's constant, which is 6.63 times 10 to the power of negative 34 joules per second. And we calculate that, and we get 1.23 to 2 decimal places times 10 to the power of 15. And that's the answer. So the minimum energy needed to emit electrons is 8.17 times 10 to the power of negative 19 joules, corresponding to using instant light with a frequency of, and we got 1.23 times 10 to the power of 15 hertz. The fifth topic is photons have momentum or the Compton effect. The key person for this topic is Arthur Compton, and he was an American physicist who discovered the elastic scattering of photons by high energy photons, or best known as the Compton effect. There is a photon momentum formula, and it is P equals h over wavelength, where h is Planck's constant. Compton first discovered the Compton effect by shooting a beam of X-ray photons at a thin piece of metal. The energy of the photons is directly proportional to their frequency and inversely proportional to the wavelength. So lower energy photons have lower frequencies and longer wavelengths. In the Compton effect, individual photons collide with single electrons that are free or quite loosely bound in the atoms of matter. The Compton effect has a very important place in the history of physics because it proves that electromagnetic radiation cannot be explained as a purely wave phenomenon. And now I'm going to derive the momentum equation. So first, Einstein's quantum theory predicted this equation to calculate the momentum of a single photon. P, or photon, equals h f over c, where h is Planck's constant and f is the frequency and c is the velocity of a wave. Then the wavelength of a light wave is related to its frequency, so it's f wavelength equals c. Then you substitute f wavelength for c in the photon momentum equation, which gives you P equals hf over c. You substitute that. Then you get hf over f wavelength. You cancel out the two frequencies. And you get P equals h over wavelength. And that's your momentum equation. The sixth topic is the Broglie wavelength. And I'll be also solving a bonus example problem. The key figure for this topic is Louis de Broglie, and he was a French physicist who discovered the wavelength associated with the motion of a particle possessing momentum of magnitude p, or otherwise called the de Broglie wavelength. According to the Broglie wavelength equation, a long wavelength equals a small momentum value. If a particle has a wavelength, the particle should exhibit interference like waves. If an electron were to be accelerated by 100 volts, it would become 0.132 Newton meters. De Broglie also concluded that all particles can exhibit wave-like attributes, and the wavelength of a particle is inversely proportional. The equation can also be written as wavelength equals h over mv, where m is the mass of the particle in kilograms, and v is the velocity in meters per second. Plugging in the values will give the value of the wavelength in meters. So this means that an extremely light particle is required, and during this time, it was thought that electrons were the lightest particles. This new observation brought forth the concept of matter waves, which is the theory that all matter exhibits wave-like behavior. And let's go over to the Jamboard and do the example problem. Winston used electrons with a kinetic energy of approximately 80 electronvolts, and the mass of an electron is 9.11 times 10 to the power of negative 31 kilograms. Calculate the de Broglie wavelength of these electrons in meters. So I know that 80 electronvolts, if you convert it to joules, it's 1.28 times 10 to the power of negative 17. And I just used the online converter for that. And we know the mass of electron, it's 9.11 times 10 to the power of negative 31 kilograms. And we know h, which is Planck's constant, and it is equal to 6.63 times 10 to the power of negative 34. And we are going to use the kinetic formula to get the velocity. So the base formula is ek equals 1/2 times mv squared. Solve it for v. So you isolate v and put it on the left side. Becomes square root 2 ek over m. And you then fill in the values. And after that, let's calculate what the answer is for velocity. And the answer is 5.3 times 10 to the power of 6 meters per second. And let's use the wavelength formula now. Its wavelength equals h over p, or h over mv. And again, we just plug in the values. 6.63 times 10 to the power of negative 4 for h. 9.11 times 10 to the power of negative 31 for m. And wait, what's it again? 5.3, okay. And it's 5.3 times 10 to the power of 6 for v, velocity. And let's calculate it. And I got 1.37 times 10 to the power of negative 10 meters for the wavelength. And if I convert that to Newton meters, it's 0.137 Newton meters. And that's the wavelength of the electrons that Winston used in his experiment. Our second last topic of the day is the Heisenberg uncertainty principle. The key figure for this topic is Werner Heisenberg, and he was the one who discovered a crucial theory of quantum theory, the Heisenberg uncertainty principle, back in 1927. A few key points. The Heisenberg principle states that it is impossible to know the exact position and speed of an electron at a given time. If you measure the position of a quantum object with great accuracy, you can only measure its momentum with unreliable accuracy. And there's a formula for this as well. It is delta x times delta p greater than or equal to symbol h over 4 pi. H stands for Planck's constant, and pi is 3.14, whatever. And take a look at the diagrams at the bottom. The first diagram shows that if there's a wide slit, the diffraction is narrow for the electron to go through. The second diagram shows the opposite, and the third diagram shows the spreading of an electron wave as it passes through a slit. That gives way to relate the uncertainty in the electron's position, delta x, to the uncertainty in momentum, delta p. And now for a final topic of the day, applications of physics in the real world, and we will be looking at the electron microscope and chip design. Did you know that electron microscopes can magnify up to 1 to 50 million times? This means that it is far more superior to its light microscope counterparts. Electron microscopes uses a beam of accelerated electrons as a source of illumination, and they are mainly used to study ultrastructure of inorganic or biological specimens, such as cells, and they are incredibly useful at studying extremely tiny particles. The first electron microscope was built in 1931 by physicists Ernest Ruska and Max Null. Electron microscopes are also very heavy. They can weigh up to 10 tons and be around 10 feet in height. They play an important role in today's scientific and medical communities. Now for chip design, chances are your device has a chip, and they are also known as the brains of computers, phones, or any device. Whether it's a computer chip to store your memory, for example, like a RAM card, or a SIM card in your phone to call and text, chips are small but complex. They are also called microchips, and they were said to be the basis of the computer revolution. Chips are usually made from silicon, and silicon is made from sand, and that's really convenient. But the process of creating chips is highly complicated, and I'm going to link a reliable video in the description so you can watch it yourself. I let the professionals explain it to you. And chips is one of the reasons why our technology has grown so advanced. And that's the end of my quantum mechanics video, and I hope you enjoyed it, and thanks for watching. If you have any questions, feel free to contact me or leave a comment, and have a good day.